Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on evaluating Bessel functions. And so far, we have looked at the Bessel functions of the first kind, and we implemented very efficient ways of calculating the J nu of x for small arguments, large arguments, real numbers, complex number, anything. And now we want to look at the second Bessel function. So the Bessel function of the second kind, which is yn or y nu. Let's start with the integer parameter. And this is also a solution to the ordinary differential equation. So the question is, why is it that we are not using... so if you look at the Bessel function, Bessel equation, the ordinary differential equation, this has x squared minus nu squared, right? And we found out that J nu of x is a solution. So I know that in this equation, if I set nu to minus nu, the equation doesn't change. So we can conclude that J minus nu should be also a solution, right? So why are you saying that instead of using J minus nu, we are using y nu? So that's a very good question. And the answer is that yes, J minus nu is a solution always, because that's just the nature of the differential equation. If I set nu to minus nu, the equation doesn't change. So if J nu is a solution, J minus nu must also be a solution. The problem here is that if nu is an integer, J minus nu and J nu, or J minus n and Jn, are not linearly independent. And if you are familiar with the theory of differential equations, you know that a linear second order differential equation must have two linearly independent solutions in order for us to be able to write down the general solution of the differential equation, right? So if nu is an integer, J nu and J minus nu are not linearly independent. Actually, we already seen what the relation is. If nu is an integer, J minus n is minus 1 to the nth power Jn. So J minus n is just plus minus Jn, right? Based on n is even or odd. And that's the reason we're defining another function, or we're looking for another function y nu, which is linearly independent always, even for integer parameter. But it is true that if nu is, or n, or nu, the parameter of the Bessel function, is not an integer number, then J nu and J minus nu are completely linearly independent, and they are two valid solutions for the Bessel function. So we can write down any general solution based on a linear combination of J nu, J minus nu, provided that nu is not an integer, right? However, we realize that once we find a definition for y nu or yn, it's actually a much nicer way of dealing with Jn and yn, because the combination of the two actually provides some very interesting properties that I will discuss in this lecture. But first, let's look at the yn or y nu. And this yn, again, it's obviously a solution of the differential equation, Bessel equation. And it also has other names such as Neumann function or Weber function. It's typically known as the Neumann function. And again, a similar approach that we took for Jn, we can also take for yn, aka we go with the integration. So yn is given as an integral function. And all these yn functions, they have the property that they go to minus infinity as x approaches 0 from the positive side. All right, so the Bessel function Jn only had this first term, a finite integral, and we could easily do it. But here we also have this infinite part, or improper integral. Okay, so yn is 1 over pi 0 to pi sine of x sine of theta minus n theta d theta. Remember, Jn was cosine, yn is sine. Minus 1 over pi 0 to infinity e to the nt plus minus 1 to the nth power, which is plus or minus 1, e to the minus nt e to the minus x sine hyperbolic of t, or sinh of t. And again, you see that this description is only valid representation of yn when the real part of x is positive. So x could be a real number, which should be positive, or a complex number which has a positive real part. That's just because of the convergence of this integral. All right, so it's very easy to implement this. The first part is super easy. So first I calculate this factor -1 to the n, which is if n is even. So I'm using a one line conditional, this one. So if n is even, I return 1. If n is odd, I return -1. So I'm using this modulus operator or remainder operator, right, for integers and longs. So this factor is basically -1 to n. And then function yn is basically this integrand 1/pi sine of x sine of t minus nt. T is just the theta. And then func yn inf, which is the integrand here, -1/pi, this coefficient, x power nt plus x power minus nt times this factor that we already calculated, times x power minus x times sinh of t. Okay, and then we start by numerically calculating this integral. So integral yn said integral function func yn, and then we can do Simpson from 0 to pi with some order, some number of subintervals for discretization of the integral, which we by default I set it to 300. And then integral yn said integral function func yn inf, this one, and here we go from 0 to some large number, and for stability reasons I just set it to 10. I mean, if x is positive, this exponential is decaying very rapidly, because remember sinh is some sort of related to the exponentials, right? So e to the exponential of something decays very rapidly because of the negative sign here. So for stability reasons, numerical stability of the integration and discretization, I'm just putting 10 here. You can set it to 20 or whatever. The accuracy doesn't change that much. So we calculate numerically these two integrals. I'm using Simpson, but you can use any other method, and return the two terms. All right, and here are the plots of y0, y1, y2, y3, and as you can see, we see these oscillations as x increases. So they behave like sine cosine function as we expect. Any Bessel function should exhibit these oscillations for large numbers. They get closer and closer to sine and cosine, and you can see it even here. So if x gets very large, we can drop this integral because e to the minus x sinh of t decays very rapidly. So we drop this, we end up with 1/pi 0 to pi sine of something, and this is more like the sinusoidal behavior, this oscillation. But when x gets closer and closer to 0, we go to infinity. That's just because if x gets to 0, this exponential term, which was the reason for the convergence, vanishes, gets closer to 1, and now we have 0 to infinity of e to the nt. Definitely diverges, right? This definitely diverges. That's why we go to infinity. So let's head quickly to Eclipse and try to do this. So in my Bessel function integration, if you recall, we had the jn, jnu, and now we have yn and ynu. And then for yn only works for integer variables, integer parameters, and this is basically the same code. Simpson 0 to pi for the finite integral, 0 to 10 for the infinite integral, right? You can set it to 20, 100. You have to be careful that the integration be stable, otherwise you get inaccuracy. All right, and I have created this test yn. So I create the Bessel function integration object, and then x goes from 0.1 to 100. I'm not setting 0 because it just cause it goes to infinity, right? And I'm creating a timer. I'm calculating y0, Bessel ynu, or let's call it yn 0, and in parameter 0 with t applies to the array x, and then we want to plot it. So let's run this. So it takes about 300 milliseconds. If you recall from our jnu implementation, we saw that the same thing happens. Implementation based on integration takes a long time, but when we switch to power series, it becomes extremely fast. All right, so this is J0, And as we see, it goes to infinity. So if I go, instead of 0.1, I go to 0.03. And as you can see, it goes more and more down, right? And if I go, for example, to 0.005, it goes more and more down, right? Eventually, when we go to 0, it goes to infinity. So this is an implementation of y for integer index. So what happens when the parameter is not an integer? Then this integral representation is not valid anymore, right? So we have to switch to another implementation. So when we want to implement y new, where new is not an integer anymore, right? So what we are going to do is we are going to use the calculate y new based on the function j new, all right? And that's another reason that we spent a lot of time developing good implementation for j new. It turns out y new has a general definition based on j new and not surprisingly j minus new, right? So y new is j new cosine of new pi minus j minus new divided by sine new pi. Now this definition obviously is correct for non-integer new. So if new is not 0, 1, 2, 3, etc. If new is an integer, then obviously the negative ones are also invalid. So 0, minus 1, minus 2, minus 3. But what I would like you to notice is that when new is integer, this sine of new pi becomes 0. That's why this is not this blows up and it's not correct. But the way we do it is, this is the general definition for non-integer new. When new becomes or approaches an integer, we take the limit. So for integer new equals n, take the limit as new approaches n. And because these Bessel functions vary very slowly with new, so if you change new by 1%, go from 1 to 1.01 or something, the value doesn't change much. We can set new to an integer minus epsilon. So if I want to calculate y1, I can set this new to 1 minus some epsilon, which is 0.01, is very good approximation or a good number. So instead of calculating y1, I calculate y.99, and it gives me a very good approximation of y1. And now new is not an integer anymore, so I can just put it here, all right? And again, we go through all this trouble of this definition, because if new is an integer, j new and j minus new are not linearly independent. But y new and j new are always linearly independent, whether or not new is an integer or not, okay? So if I want to implement y new for double new and double x, so I check whether or not new is an integer. So take the absolute value of new and downcast it to integer and see if the result is greater than, the difference is greater than some tolerance, let's say 1e minus 5. If that's the case, I assume that we can set it to minus 2. Then I assume that it's not an integer anymore, so I return j new of nu and x cosine of pi nu minus j nu of minus nu and x divided by sine of pi nu. All right. Now you notice that in order to calculate y nu, we're basically calculating the j nu twice, right? Two Bessel evaluations. And as long as we have a very fast implementation of j nu, then we are good. We don't need to worry about the numerical computation or the cost of evaluating y nu, right? So if we determine that nu is an integer, so then we invoke yn. And again, for integer n, yn is the limit of this expression, j nu cosine of pi nu minus j minus nu divided by sine of pi nu when nu goes to n, or when nu approaches the integer number. So here's an example of y nu for non-integer parameters, 0.5, 1.2, 2.9, and 3.4. And again, I implemented these from this relation, and in this relation, I'm using the integral implementation of j nu, all right, that we had. So again, we see the oscillation behavior, which is good, and we see that the y functions go to infinity, minus infinity, as x approaches 0, which is correct. So and in fact, for non-integer numbers, non-integer x values, this thing that goes to infinity comes from the fact that j minus nu, when x goes to 0, approaches 0, j minus nu approaches plus infinity. And because we have this negative sign, this goes to negative infinity. Because j nu of x doesn't have any singularity, right? So it always is for if nu is not 0, j nu of 0 is always 0. So y nu of 0 is minus j nu of 0 divided by sine of pi nu. So the reason this blows up to minus infinity is because j minus nu of x blows up to plus infinity at x equals 0, all right? So let's head to Eclipse. In the Bessel function integration, I have this y nu, which I look at the nu and determine whether or not it's an integer. And if it's an integer, and the way I determine it, I just downcast nu to integer and calculate the absolute error between nu and integer nu. And if it's less than some error, let's say 1e negative 10, for example, or whatever tolerance that you want to use, we invoke the integer function here. Otherwise, we use the j nu relation. And this j nu is in this object, so we are using the integral implementation of j nu in this function. And to refresh your memory again, if we go back to one of the lectures about j nu or j alpha, when alpha or nu is not an integer, then we also end up with the 0 to infinity integral, all right, e to the minus x sinh of t minus alpha t, sine of alpha pi over pi, all right? And we implemented this. All right, so let's just quickly test this as well. So maybe I'm going to create test 2 here, and I want to run test 2 public static void test 2, and here I'm going to copy and paste this. But now instead of yn, I'm going to invoke, first of all, I cannot invoke a double on the yn, because yn only works for integers, so I invoke y nu, all right? And this y nu basically invokes 2 j nu evaluations. So let's see, test 2. As you can see, it takes more time for evaluating, and as expected, this goes to very infinity, and we get this oscillatory behavior. And again, we can quickly go to export to Python and test the accuracy against Python. So let's export this to a text file, and then I'm going to open it in a text editor, copy all the text here, and then go to my Jupyter notebook, right? And then paste the x and y values, and then plt plot x0 y0 color blue, and then label Java, all right? And plt legend, we're going to turn the legend on, okay? So this is our Java, and then we are going to do the same thing for Python. And for Python, I'm using the special package in the SciPy. So instead of y0, we say that SciPy special and y nu, okay? Y nu of x0, and with the color red, and we're going to also give it a line style. What is the error here? Oh, okay, we need to give the index. The index was 0.5, and as you can see, we get a relatively perfect, very good match to the. So let me just zoom on one of the parts of the plot, for example, the start part. So xlim is from 0 to 5, for example, from 0 to 10, from 0 to 20. So as you can see, the accuracy is pretty good. All right. So this is the implementation of ynu based on the integration, right? For integer, we directly calculate the integral. For non-integer, we rely on the implementation of jnu. Okay, but then obviously we spent quite some time developing the Bessel function implementation based on the small argument power series and large argument, and then we implemented the whole Bessel function, and this was extremely fast implementation based on power series, right? So what I'm going to do, obviously, so here in the next slide, I'm just comparing the accuracy of our Java implementation based on integration with the Python, SciPy, and for both integers and non-integers, you see that we always get a good result, right? But then obviously we want to go and use power series, and again, what we're going to do, we're going to rely on the general definition. So for small arguments, we had a very nice and very fast power series or sequence calculation for jnu, which also works for j minus nu, right? And also works for complex numbers, but we have to be careful a little bit about the phase and the quadrant. Look at the phase, for example. Let's write it here. What I mean by that, you have to, this equation for jnu of x, when x is complex, you have to, it changes a little bit when x in different quadrants, i.e. the phase of x is in first quadrant, second quadrant, or third or fourth. You have to be careful, right? And then so this is the general definition of ynu and works for any nu non-integer. For integers ones, we take the limit, right? But for large and we can use for a small argument, we can use this general definition, calculate jnu for small arguments, and then calculate ynu. For large argument, we saw that ynu actually has an asymptotic similar to jnu. Jnu had an asymptotic which was some amplitude, cosine of some phase. Ynu becomes the amplitude times sine of the phase, right? But here for simplicity, because again our implementation of jnu is extremely fast, we don't care if we calculate jnu once or twice, right? So I'm going to rely exclusively on this general definition and calculate ynu solely based on jnu. So here's the code. It's extremely simple. So when we want to calculate ynu, we, for double nu, for any double, if we check if nu is an integer or not. If it's an integer, we return, if it's not an integer, we return j nu of nu and x, cosine of pi nu minus j nu of minus nu and x divided by sine of pi nu. All right. And again, if x becomes complex, the definition doesn't change. So that's a plus in terms of implementing this way. And else, if nu becomes integer with this threshold 0.01, then I define the epsilon 0.01, right? And then instead of evaluating the right hand side here at nu, I evaluate at nu minus epsilon. So instead of evaluating at 2, I evaluate at 1.99, which always gives a good approximation of 2 of y2, right? So what I'm saying is that y2 is a good, y1.99 is a good approximation of 2. The error is very small. So I calculate the right hand side for integer, all at nu minus epsilon, right? Cosine of nu minus epsilon times pi minus j nu at minus nu minus epsilon and divided by sine of pi nu minus epsilon. All right. So let's head to Eclipse. And in Bessel function, I have this ynu, and the thing was that Bessel function for small arguments could not return a double value when x was negative and nu was non-integer, because the result becomes complex. That's why I'm checking whether or not, if nu is non-integer and x is negative, we have to go to the complex implementation. That's why I'm saying that ynu cannot be calculated past x as a complex number. But then if nu is non-integer, I'm calculating the relation. If nu is integer, then I'm calculating this relation. So I have this test y nu, and this one relies based on the fast calculation of Bessel function. So y1, I calculate my Bessel function object from 2 to 100. I'm calculating y nu from with the index nu is minus 5.5 x, and maybe let's change this to y nu. And this y nu comes from our fast evaluation from j nu, and j nu comes from j nu a small argument, j nu large argument, right? So let's first look at the y0. So in our integral implementation, we know we calculated y0 from 0.005 to 100. So let's do a direct comparison. So for power series expansion, we get 35 milliseconds to evaluate y0 for 1000 points, right? And for in numerical integration, integral implementation, we get 300, so a factor of 10 improvement in the speed of evaluation. And these two basically return the same result, right? The accuracy is the same. Actually, power series is a little bit more accurate, but the main thing is about going from 300 milliseconds to 30 milliseconds. So a factor of 10 improvement, which is a huge improvement, right? And then here, let's also run test 2 here. For non-integer ones, maybe let's still keep test 1. And for non-integer ones, let's run from 2 minus 5.5. It takes 33 milliseconds, and this is y nu, where nu is minus 5.5. all right? And let's see if we can run this one too. Here we had a y nu minus 5.5 and from 2. So for integration, let's see if this works. It takes 500 milliseconds and it returns the same thing. So it's even more than a factor of 10, because for non-integer evaluation using the integral, we have to calculate 2 integrals. So a factor of 12, for example, right? But the results are basically the same. So power series is the way to go, and we will definitely use it when we calculate the Bessel functions. And here's the case for complex numbers. In test 2, I'm calculating from 2 to 100, y nu minus 5.5, and x goes from 2 to 100, and I'm taking x, reversing the sign and adding minus 2j to it, right? And then so only the real part is changing, the imaginary part is constant, and we plot both the real and imaginary part. Takes 84 milliseconds. This is the real part and imaginary part. The blue is real part, and we can export it to Python and compare it with the Python results. So I'm going to open it in a text file, and let's go to our Jupyter notebook here, paste the result. So y0 is the real part, y1 is the imaginary part. So y nu, and let's see, we're calculating minus 5.5 and minus x minus 2j. all right, so this is minus 5.5, and here I have to basically convert this to a NumPy array, so I can use the operator overloading support, and then minus this, minus 2, 1j, right? But then this returns a complex, so I want to plot the real part first, and let's just remove this part. All right, so this is the real part, and if I want to plot the imaginary part, I use y1 and numpy.image, and this is the imaginary part. All right, if I want to plot both real and imaginary part at the same time, that's real image y1, y0, blue y1, let's say k, and we can have red and green, for example. So we have the real parts and imaginary parts, they match perfectly, and it took us only about 80 milliseconds to calculate 1000 terms, which is very good, very fast. All right, so we are almost done with Bessel functions. There is the last thing that I would like to discuss is the Hankel function. So as I mentioned, J nu and Y nu show sinusoidal behavior when x is large, and J nu was amplitude cosine of some phase, and Y nu was amplitude sine of some phase. So if we add plus minus j and calculate this J nu plus or minus j Y nu, we end up with the amplitude times exponential of j phase, right? And the beauty of these terms, which are called Hankel function of the first kind and this Hankel function of the second kind, is that when you have a phase e to the j something, it shows a propagating wave, right? So Bessel function J nu is a cosine of some phase. That means it's a standing wave. But then when you have e to the j phase, a complex exponential phase, it means you have a propagating wave. That's why when in the wave solutions, in the wave equation, when you want to represent standing waves, you use J nu and Y nu. When we want to represent propagating waves, we use Hankel 1 and Hankel 2. So these Hankel functions represent radially propagating inward or outward cylindrical waves. Hankel 1 is a wave that comes towards the center. Hankel 2 is a wave that goes from the center outward to infinity, right? And as you can see, we have two evaluations of the Bessel functions. These are the definitions: e to the j pi nu, sine of pi nu. And again, it's better to use this definition instead of calculating J nu and Y nu first. And the reason is that we already have two J nu evaluations in the Y nu, right? So if I want to calculate Y nu first and then J nu and then combine them, I get 3 calculations of J nu, right? Because Y nu already has 2. But when I write down the actual equation, which comes from the definition of Y nu, then we see that we still have 2 Bessel function evaluation, J nu, J minus nu, but some complex exponential, which is very easy to calculate. So it's actually better to calculate the Hankel functions directly from this side instead of calculating Y nu and J nu first, all right? Then we always end up with only 2 Bessel function evaluations. So we're going to use the direct definition based on J nu and J minus nu. And again, for integer nu, when nu becomes n, take the limit, which means take an epsilon, very small, and use n minus epsilon. But remember, this Hankel function should always return a complex number. That's why we don't have here a public double version. Hankel 1 but x can be a double value, a real number, or a complex number. But Hankel functions always return a complex number. So double nu is double, and x could be a real or a double or complex. Here I'm assuming a complex. And if nu is not an integer, 1 over j, I'm bringing to the top, it becomes minus j times j nu minus nu x minus complex math dot exponential minus j pi nu times j nu divided by sine of pi nu. All right. For integer 1, then I replace nu by nu minus epsilon. So for example, if I want to calculate Hankel 1 when nu is 2, I calculate Hankel 1 when nu is 1.99. And that gives me a very good accuracy. All right? So let's go to Eclipse and go to our Bessel function. I have this Hankel 1 and Hankel 2, Hankel 1, this, and Hankel 1 when x is double. Again, the implementation is exactly the same for double and complex, because our J nu doesn't care if x is real or complex. The caveat is that we have to be careful when x is double, because we have to invoke the J nu when pass x as a complex number which has a 0 imaginary part. So we cast x to a complex number and then pass it to j nu. All right. Hankel 2, the same thing, similar implementation. So basically the difference between Hankel 1 and Hankel 2 is that whenever you have j in Hankel 1, you replace it with minus j. So minus j becomes j, and minus j in this exponential becomes j in this exponential, and that comes directly from definition. Just be careful. This doesn't mean that Hankel 2 is the complex conjugate of Hankel 1, because x could be complex, or even if x is not complex, if nu is negative, if nu is a real number and x is negative, basically if nu is not an integer number and x is negative, j nu becomes complex, even if x is a real number. So be careful. Hankel 2 and Hankel 1 are not complex conjugate of each other. It's just the fact that you put the j to minus j, all right? Only when j nu of x and y nu of x are real numbers, Hankel 1 and Hankel 2 are complex conjugates of each other. So I want to make sure that you understand this. The way to go from Hankel 1 to Hankel 2 is to wherever you have j, you set it to minus j. So in this definition for Hankel 1, here I have j here, e to the minus j, I set it to e to the plus j, all right? And then j in the denominator becomes minus j. And then we combine minus with the numerator, it becomes e to the plus j pi nu j nu minus j minus nu, all right? So whenever you have j, you set it to minus j. And then again, we can have Hankel, which directly takes a complex number. And here's a test that I wrote for Hankel. I'm creating my Bessel function object, and Hankel x from minus 210 to 10. I calculate, I don't even need to have this part, because in the implementation, I'm already casting x to a complex number. So Hankel 2 returns a complex number, and we're plotting the real part and imaginary part. 85 milliseconds, this is the real part, and you see this discontinuity here. So the imaginary part goes to infinity, and the real part ends up with a discontinuity here, right? So let's export this also to Python and compare the results. All right. And here, let me just, and here instead of scipy y nu, I'm going to call Hankel 1, right? And Hankel 1, what was the index that we use? 0. So index 0. And again, the imaginary part of Hankel 1 with index 0. And I'm passing it x0, so there's no need for all of these. x0. All right. Okay, we calculate Hankel 2, not Hankel 1. So Hankel 2. All right, as you can see, we see exactly this discontinuity. And then also the imaginary parts, they match very well with each other, okay? So I hope you enjoyed this lecture. We are almost done with the evaluation of the Bessel functions. And please stay tuned, and I'll see you in the next one.